The purpose of these videos is to review some of the ideas of Taylor series from class. This is a sequence of 4 videos. I suggest you watch them in order. Video 1 is a little bit more of an overview of some ideas. Videos 2, 3, and 4 go through some examples, and video 4 does a little bit of wrap up at the end too. So to compute to compute a Taylor series, it's a special type of power series. You need a function and an x value a. And one method to use, it's really fast if you can do it, is to use the geometric series formula. I'm using b for the first term and r for the common ratio. And here's an example of that. So this equal sign right here, this only works as long as, well, the common ratio here, the absolute value of that should be less than 1. But the thing is, sometimes you can't relate the function you're dealing with, the function you're given, to geometric series. Or maybe you can, but you just don't see it. So there's a more general method which should work all the time. There are some exceptions, but here's what you do for that second method. You compute every single derivative of the function you're given, evaluate each of those derivative functions at the x value a, define these numbers c sub I. These are going to be the coefficients of x to the ith power, and they're the numbers you computed right here. Just divide by I factorial, and then finally you just piece this together and make the power series. Finally, there's a thing called a Taylor polynomial, which is not all the terms of the power series. It's a partial sum. Just take up to term number n, so stop at some point, and you'll just have that. So that's T sub n in the Stewart calculus book. You can, just as an overview, get new Taylor series from old Taylor series. So we're just going to kind of go through some of the ideas here. This will be a little abstract, but then you'll see how this works in the example. So let's say you have a power series. You have a Taylor series, which represents f. Then if you're looking at an antiderivative, right? So if g is an antiderivative, that means g prime is equal to f. Then you can get a Taylor series for g. If you have one for f, all you have to do is just integrate. And you can integrate one term at a time. So the point is this, you're just adding up a whole bunch of things which look like c sub I times x minus a to the I. Just integrate each one of these. And this is going to just be a simple u substitution. U is equal to x minus a. And so what happens is this I goes up to I plus 1, and you divide by I plus 1, and that's it. Same thing, if you have h as a derivative of f, then you can take the power series for f and just differentiate term by term to get a power series for h. And there's a couple other things you can do. Algebra, for instance, let's say you have a function k which is f of x times an x. Well, then you get a power series for k just by multiplying by x, and you can distribute this x all the way in here. And there's a little typo. This should probably just have an x. You'll see in the examples later. And finally, if you had a new function p of x, which was just take your old function and you want to square the input, just substitute. Every time you see an x, like right there, replace that with x squared. And we'll see examples of all of these things later on in the slides. So one example, let's say you wanted a power series representation for arctangent of x. Well, let's take a look at the derivative of this and call that f. Here it is, and you can rewrite this. And here, think of this as a sum of a geometric series. R is equal to negative x squared. That's in parentheses here. So the convergence will occur as long as, and if you work this out, this will be as long as x absolute valued is less than 1. So if that's true, then this right here is the geometric series sum of this geometric series right here. Here's the common ratio raised to the ith power. And you can rewrite this a little, just algebra for the inside, and then apply the ith power to each of the factors here separately. And this is a nice sort of standard way to write this power series. So let's summarize that. If f of x, which is 1 over 1 plus x squared, that will equal this power series here, but that's true, well, due to this, as long as you're looking at x kind of close to 0. It must be distance less than 1 away. And now we can integrate. So if you integrate f, you get g, and if you integrate here, well, there's a plus c, but then what happens? You integrate here term by term. This is just a number, negative 1 to the I. That's some coefficient. And then you have the power of 2i gets raised by 1, but then the power rule in integration says you should divide by 2i plus 1. We need to figure out what c is, so what we're going to do is plug in a 0 for all the x's. So this x became a 0 right here, and that's, well, just a definition. This is arctangent of 0. And this x right here also became a 0. And if this is a 0 right here, guess what? You're just adding up a whole bunch of zeros. So you actually get just a c on the right side. You get just arctangent of 0 on the left side, which is just 0. That tells us that c is equal to 0. So I left this plus c out this time. And then, so all this step did, by plugging in x is equal to 0, we found out what c had to be. So then we can go back a step. G of x, which is arctangent of x, is actually this power series. Second example, let's use 1 over 1 minus x. We saw this geometric series on the first slide, and now let's look at the derivative of this, which looks like that, due to quotient rule or whatever you like. And so we saw this geometric series earlier for 1 over 1 minus x, and now we can differentiate term by term. So if you differentiate f, you get h. That's right here. Okay, f prime is h. And then if you differentiate the 1, you get a 0. If you differentiate the x, you get a 1. If you differentiate the x squared, you get a 2x. Differentiate the x cubed, you get a 3x squared, and so on. And if you stare at this for a while, maybe ignore the 0, and then the rest of these terms, just by doing some pattern recognition, you should get this power series right here. That's the end of the first video.